be that a drilling engineer has to do also with water wells, and there are some specific conditions. And then I will try to give you a kind of summary. This is directly preparation for the examination. It covers not all, but covers a little bit the topics for the examination. So let's start with this brief look in the water exploration. Water exploration wells are not subject of the examination. There are some specific things. If we have a water well, we have at first, in many cases, relatively analysis. Many of the water wells depend on the geography and the hydrogeologic situation of the country are wells in unconsolidated formations. This has, in terms of the geology, a second consequence, and the second consequence is most of our algorithms, Wiley's equation, Archie's equation, are working very well if we have consolidated typical sandstones. If we have unconsolidated sandstones, we must apply any modification or any correction. Second situation, different to what we discussed, normally in the pore space is water. This is what hydrogeologists are looking for. And the water is fresh water, hopefully. And fresh water, this has, for our interpretation, an important consequence. Fresh water has resistivity, high or low? High resistivity. Therefore, we have a different situation with respect to the resistivity, and we have a very, very high sensitivity if shale is present. Remember always, shale and the water in the pore space are the two conductors. If the water has a high resistivity, then a moderate or a low resistivity of the shale determines what's the situation with respect to the current flow. We will not forget there is in the unconsolidated formations a more technical problem. Unconsolidated formations, normally you drill, and after a very, very short time you must complete, because in other case it's collapsed. So you have only a very short time for any open hole measurement. You must reduce your program, and you must be fast. You must be, if drill operations are finished, you must measure immediately, and you must be out of the well before it's collapsed. And then we will not forget water wells compared with oil or gas wells are always a job with a very, very low budget compared with the oil industry. So if we speak about water exploration, and we remember there was this nice nuclear magnetic resonance tool for permeability, it works very well in the sand, yes, but you can't forget it for the water exploration. No company will pay for it. So you must run with a very small budget and with a reduced program. The problem, or the problems we have to solve, are listed here. In most cases, it's a lithologic profile, the determination of the depth and the thickness of the aquifers, and this is all. If you have determinist, you find here no number, no parameter, no quantity. It's not the job to determine the porosity. If you have a sand, there is porosity. The only parameter which would be of interest is permeability. But at first, permeability is too difficult to determine. Difficult, it means too expensive to determine. And on the other hand, it's also a specific situation in this part of the industry. For water wells, permeability, hydraulic permeability is determined by a test. It's a pump test. And normally, drilling company is doing also the pump test. So the drilling company is not interested to apply any other technique than this direct standard measurements. You see gamma log and resistivity log, and we will see with our few examples. This is a very powerful combination. Very powerful combination. Also, therefore, because we can run gamma log and simple resistivity logs with one tool, so it's only one measurement. Then it's measured normally with the water temperature and the conductivity. Water temperature and conductivity gives you an information what's the salinity and what's the quality of your water, and the caliper for all the things we now have with respect to the stability of the water. A special part is also for this, I will show you two examples, is fluid logging in water wells. Fluid logging is not directed on the determination and characterization of the formation, the lithologic profile and so on. It's directed on the properties of the fluid of the water and also on the motion of the water, the fluid flow in the underground. What I have, it's not necessary. So, geothermal projects, temperature measurements are very important. Contamination is also important. If you have a contaminated water, a good indicator is the conductivity of the water. Normally the conductivity increases. Some years ago we started a permanent borehole measurement system in the Ahrtal near Innsbruck. It's a very contaminated zone, and around this was a series of wells, and we measured only the resistivity. It was the most powerful instrument to observe what's happening inside and what's happening outside. Water motion is still a problem. With respect to the water motions, the horizontal fluid flow, maybe you know Artur Garayev. He finished his master thesis 5 weeks ago or so, and in your department he designed a very nice instrument. This is an example. It will demonstrate most of the things we can do if we have a water well in such an unconsolidated profile. It's from southern Styria, a water exploration well. Later on it was, part of this is what it was a production well. You see here one measurement in the open hole. Open hole measurement gamma log and open hole measurement resistivity logs. Two simple resistivity logs, 4 electrodes, no induction log, no laser log. It's all too expensive. Also electronically too expensive. And I think we can understand the logs if we go from 150 meter up. You see here is a section with low gamma radiation and a high resistivity. Low gamma radiation, high resistivity. Low gamma radiation, high resistivity, and some smaller going up. How we can understand or how we can integrate this tells us from the mineralogy. There's probably less shale. It's probably the aquifer zone indicated here. And the dramatic increase of difference in the resistivity comes from the difference between the low resistivity of the shale zones with the clay resistivity or clay conductivity and the relatively high resistivity of the water saturated aquifer, but the water is fresh water with a high resistivity. So this situation is a very good indication for such an application or such a detection of the aquifers. Here is a drop in the gamma log, and there is no resistivity. This is also typical in many situations of such wells. We have here the steel standpipe, and we cannot run the resistivity log, and the gamma log is attenuated because the steel absorbs the power of the gamma radiation. Normally, the result of such a measurement is recommendations for the design of the completion, because immediately after the measurements, the well must be completed. In other case, it's normally collapsed. And for the completion, it's important to give the company or the drilling engineer an information. A screen makes sense here, a screen makes sense here, maybe also a short part here, 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 and in the uppermost, this comes from the cutting material, the caving material from the uppermost part. Of course, we have here no representative measurement of our logs. If you think in this situation, the technician with the logging truck is on the well side, is doing the measurement, producing a simple black and white hard copy or plot, and then together with the drilling engineer or the boss of the drilling company, he will design this completion for the well. It must be done again immediately, and therefore this notes on the hard copy is like a document. The written report coming 2 weeks later or so, it's only for the archive. For the decision, it's important to have this. Therefore, if you are in this business, you must have a very clever logging engineer. The logging engineer must be able to support or to give the first interpretation with the possibilities we have today to transfer the data directly to an office. It's possible to give him some support, but again, it's an important job for him. Then the well was completed, and after the completion we have the possibility, and this may be a little bit specific, for the water wells to control all is okay, yes or no. And what does it mean all is okay? Okay is the screen parts in the correct depths, and the screened parts are hydraulic active. It means they must be permeable. Not only the screens, it must be also a permeable zone in order to produce the water from the wells. For this, I hope it comes with the next. Oh, here we have a little bit color. Here we have again the zones. Then the design for the well, and then it's completed, and after the completion we can control for the control measurement. Frequently used is temperature. It's also possible to run the temperature measurement in the open well if you have enough time to understand such a temperature curve. It's helpful to discuss it going upward. If you go upward, you have here the normal temperature gradient, then you have like a step or like such a plateau. This is typical if water comes in and goes up, depending on the flow rate, and we have this more or less long, short or long plateau indicating a water inflow. This is an indication. In some textbooks, you find recommended techniques to calculate the flow rate from this. This is an overstress also with respect to the theory and the practical conditions. If you will calculate from this step the flow rate, you must know exactly the geothermal gradient at this position without an inflow, but you have not this information because you have the inflow. So your reference is a question. And it's also not necessary for the practical application. Typical for water fluid logging are flow meters. Flow meters are nice instruments. It's my experience if we discussed a logging program for any water project with several wells, it was hard to explain our partners why we need resistivity, why we need a gamma log, maybe we need also a gamma density log. With the flow meter, there's no discussion. It's immediately to understand. What's a flow meter? A flow meter is a tool at a cable, and the main part of the tool is an impeller. And the impeller rotates depending on the speed of the fluid. So you measure the rotations per seconds, and the rotations per seconds calibrated are a measure of the vertical speed of the fluid. Flow meters are applied also in the oil industry, of course, for the water industry, and they are very, very important in two directions. We have two modes. We have one mode. Think here is one aquifer, and artesian water comes in. Artesian, it means it has a natural gradient going up, and typical for Upper Austria and also for Styria. And here is a second, not so strong. If you go down, you will measure at this position a very high flow rate. This high flow rate has three components. One component is the flow contribution from this aquifer. Second is the contribution from this aquifer, all the water goes up. And the third is, not forget the third is the component coming from the motion of the tool itself. You can manipulate all the measurements by changing the speed of your tool. Therefore, if you are in such a situation, never accept a flow meter curve without a registration of the speed of your tool. So we have this step represents this inflow, this big step represents this inflow. If you have such a measurement, you can handle it very simple and fast. You plot a line in this direction along the speed of the fluid, of the tool contribution, and you have here the maximum covering all the inflows, and then you can say, oh, this is about 60%, and this is 40% or 30 and 70% of the total what I get as a production rate. This is one for profiling. And another important application or mode is to check the function of your screened parts. You have here the full tube, and here it's screened with gravel pad behind, and the job for this screen part is to allow the water to come into the well. If you go with the same tool downward, we add normally such a pucker disc to close the gap between the screen and the tool itself. Then in the uppermost part, all the water must cross this section, and you will read a very high rate of rotation in pattern. You come with this tool in the screen part, and the screen part is okay, it's perfect. And then a part of the water will be displaced and will go around, crossing the screens and the gravel, and jumps the measured rate down, and this difference is a measure for the permeability or the hydraulic function of your screen. If it's a straight line, then it's ideal. It tells you it's a very homogeneous, perfect, screened zone. So we have these two applications, and we will have a look on the two applications in our example. Temperature, we will read it as the last. Here we have a flow meter measurement down going. This means without a pump, rotations per second. And you see the first, the second, the third, fourth, and fifth. Exactly on the position determined from the lithologic logs. They are also indicating the screening at the gravel pack is correct. Here is a small jump or a small change of the direction. This comes because the water in this dominant aquifer is a little bit artesian. So this is the first answer. All is okay. It makes sense for big wells or for expansive construction of the wells to take such a measurement immediately after the construction, then you have a reference. If after some years you observe there is a decrease of the production, you can run a second measurement, and the second measurement you compare with the first, and you can detect which part of the well has changed or is alterated or any other defect. Then, in the last track, we have a profiling. We bring a pump in the uppermost part, and below the pump we have our flow meter. This is a critical step in such an observation because it needs time. Think what we must do. We must bring the flow meter in the well, then you must hang the pump into a depth, then you run your measurement, and you must bring the pump out, and you get the flow meter out. So it's a little bit time consuming, and it needs some preparation that it runs relatively fast. You go down, here we have the highest flow rates. This is the total production of the well, except this. And here it goes down. It's the same effect we had before. Down, 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 and here we have only the final situation, practical, no inflow. Here are our screens, and then we can calculate. I hope it comes. Yes. This difference tells us what's the inflow from this zone. This difference the next, this difference the third and the fourth, and we can calculate what's the percentage of the total production. So this is a very simple technique, not comparable with the sophisticated tools and interpretation algorithm for the oil industry. Last, the temperature. You have the change of the temperature here and the change of the temperature here. At first, it tells you here and here we have two different types of water. Here is no conductivity measurement, probably also the conductivity is different. And the law for the water production and the exploration is you never connect two aquifer systems. You have here one and you have here a second one. For an exploration well, it's not a problem, but for a production well, it would be a problem, and it's not allowed to use this as a production well. If you will produce from both horizons, the only practical solution is fill the well and use only the uppermost part, drill a second well, and screen only the lower part. This is the only practical solution. Remember, this is a shallow well, and it's drilled very, very fast. fast. This is not the problem in the oil industry. The big problem, if you decide, oh, we have two horizons, please use the first well only the first, the uppermost, and then drill a second well for the second. It's out of any practical idea. This is an observation well. It has some links to, I think, yes, it has some links to the oil industry. It's in the vicinity of Spectral, but has to do nothing with oil. It's for water exploration. And you see here such a profiling. This is the uppermost part. Here comes from the filter screen the main inflow, here inflow. So all the different parts bring an inflow, and you can bring profiling and a complete check of the well. Another water well, not in unconsolidated, but in consolidated in carbonated rocks. It's at first low, and you know it's not oil what we get at first level. It's special water, and the water comes from the karstic part of the carbonate. In the uppermost part of the profile we have a brexit, then we have dolomite and limestone, but this is a result of our interpretation. Let's have a look on the selected curves. This is a gamma log, here is a resistivity log, and here is a sonic log. What we see first from the gamma log, we can separate the brexia. A brexia has also some clay material, some shaly material. We can separate it from the clean, nearly clean carbonate. So here is our carbonate. No answer, it's limestone or it's dolomite. The question is it of interest, yes or no? More of interest is where is a porous zone, in this case where there is a fractured zone to deliver the water. And for this, it's very helpful to have the resistivity. You see low resistivity in this carbonate section, high resistivity in this carbonate section. So if we have fractured zones, water-bearing zones, then we have some water-bearing zones here. There was measured also in acoustic log. It was not allowed in this well to run a gamma-gamma density and a Neutron log. This combination with active sources was not allowed. It's no danger for the water you drink because it's no contamination of the water, but it's a danger if you have loss of a tooth. And therefore, it was measured acoustic log. Velocity in the fractured zone is very, very low, and the velocity in the non-fractured dense zone is very high, and this level of 6,000 and more, it's typical for a dense limestone. It's not typical for a dolomite. A dense dolomite must have higher velocities. Though our information from this more or less static measurements, our fractured zone is here. Then was measured the flow meter downgoing. You see here we have all with a pump, all what's coming out. The change is here because we have here the inflow of the water, then it's constant because there is no more water from the lowermost part. So for the production, it makes sense normally to drill a well up to this depth. The deeper parts are not productive. We believe what we can see. This is an optical picture from the borehole wall. This is fractured zone. It's dramatic. This is not an acoustic borehole telemeter and not an electrical scan. This is really an optical because we have clear water, and in a clear water we can observe the borehole more with an optical system. If you have mud in the borehole, hopefully first level has never mud in the borehole, then you cannot see it. So you have this fractured, so it's very well and nice to see. This is another example. It's not in your material. Here was measured the gamma logs, the two resistivity logs. You see here also the same situation. And we measured simultaneously a spontaneous potential. The spontaneous potential, if in a water well is indicative, it gives you a first signal. If you measure a spontaneous potential, you have a difference between the mud or the fresh water in the borehole and the water of your formation. Maybe the formation water has some salinity, and the salinity unexpected was very high in this part, and this water well now is used for medical applications. It's not drinking water, it's for earth applications. This is, I think, it's a very bad situation from the point of view of the drilling company, yes, to construct this well. It was a water well, and the water well has a very low production, and therefore there was a big struggle. Why is it? And what's the origin, or what we can do? Here is a flow meter measurement. We can understand it immediately. We have a low flow meter rate. This is probably well screened. We have a high flow meter rate. This is the non-screened part, and then we have this part with some fluctuations from the construction of the well. This should be a screened part. But we see the hydraulic function is not okay. If the hydraulic function is okay, it must go this way. There was one more partner in the struggle. It was the logging company. It's nonsense. We cannot believe this, of course, because...
How many meters is this?
Sorry?
How many meters is this? It's not 35.
This is meters.
Okay.
You know,
so
it's very shallow.
Okay.
Yes. And therefore, there was ordered optical inspection, a camera, and you see here such a, they have very nice systems for these cameras. You see the uppermost part, if you into the well with the steel casing and the screens are open, it's perfect. It's a textbook example. Then from this part, you see, yes, no screens, there's a tube, maybe some corrosion. Corrosion is not good for a new well, but you see it here. And then you see, yes, okay, it's screened, but it's hydraulic, not effective. The screens are closed. There is some shale behind the borehole, and the bladder pack was not okay, and the shale or the clay was pressed by the earth pressure at the back of the screen part, and then we move with our tool, with our flow meter, and along the screen turns, and we publish it. And so it's completely closed. Question I cannot answer what we can do in such a situation. We can do nothing. You cannot repair it. You must bring out all the tubes, and so it's better to put a new well. This was the end of the story. Maybe it's one of the most important. Is from the brewery in Graz. Flow meter measurement. For the brewery, they use two horizons, and the job was to investigate the two aquifers, because for a new well they must decide it's necessary to down, or it's sufficient to have the uppermost. This is 70 and this is 100 meters, so the difference is not too big. It's both used again, and you see here, this is not very homogeneous, but very good permeability. This is excellent homogeneous. Maybe it's more fine-grained and the permeability is not so good. What you see here, what do you think, what is this? It's a good quality control.
It's the joints from
the connectors, yes. They change the cross-section and therefore they change also the local speed. So these are normally standard differences. You see 80, 90, and this is 3, no, more than 3, 4 or 7 meters. I think this is my last. I like this measurement. You see, behind this is number 3. It's a very, very old well. From a farmhouse in Austria. It's an artesian well. And for this well, we have also the geological description, 10 meters low. Then we have this typical shaly material, shear, and then we have clay, and again shear with some sand, and you can feel how happy people are. Finally, in 92, 93 meter, we met the sand with some artesian waters. They also measured the temperature. So this well, all the years was producing and serving for the farmers, and then in the neighborhood was drilled a new well, and then there was some conflict. They had the feeling our flow rate is decreasing. This is because the neighbor has drilled a well, and you can imagine what's the situation. We made a measurement, and this, it's a steel cased well, and here we have the gamma log. You see it's the gamma log, all the shear and the shale typical. And then, remember, it was 92, 93, the sand began. It's artesian with the aquifer with artesian water. So this is the water producer, this is not the water producer. We run also a temperature measurement, and the temperature measurement is a red line. It increases a little bit, then it increases stronger because there is no water motion in the foremost part. Then we made a measurement from the first view. A little bit stupid, an electrical measurement, production of measurement, stupid in our case now. What we can read, we can read nothing, but we could see something. This is the uppermost level of the conductivity. This is not the resistivity, it's the conductivity. Extremely high, the threshold of the system. It indicates, yes, there is a steel tube. It stops here. This is the end of the steel. And now we can understand a little bit more. What's the situation? It's interrupted over the years, more than 100 years, by corrosion. Probably it's not only corroded, it's only moved down because the drill stopped at 92. Case. If he met the water, he will not waste a full tube complete the well. So this is interrupted, and it was over all the years, the decades, moved down. Here is a piece. see dots. So, and this is permeable, and therefore a flow meter log, as a correct flow meter log must go so this step and then it full tube a straight line. But we have in all these interrupted or in all these segments with a strong corrosion, we have an inflow from the side creating this upwelling level. What's the conclusion? The conclusion is the degree at first. The decrease of your production rate comes because you are no longer in the productive horizon. A technical solution would be eliminate this part, then it's again open. The real practical solution is drill a new ground. Yes. I think more than 100 years. It's okay. No horse would work so long. But okay. With this I would close it. There is a little difference or a big difference for the oil industry and the water industry, deep and shallow, mostly consolidated. This has a consequence for our algorithms. Mostly freshwater mineralized. This powers the information coming from the resistivity. And this is also for the practical application or the practical work important. The workflow in the oil industry implements log measurements, and therefore with the drilling engineer, the petroleum engineer, you have a partner understand what's the job and what's the effect or what he expected from such a measurement. In the water exploration situation is different. It's not a critic most of what I say now. Many water wells, also for mineral water or thermal water, your partner for the discussion, also to discuss with him what's necessary to measure, is not the drilling engineer, it's not the petroleum engineer, it's the owner of the hotel, for example, and he has a completely different position to this. The longest discussions I had on our logging programs with Mr. Rodner, and it was a hard discussion. Not for him. So, and again, here you have the background, the economic power of an industry, and here is a local budget situation. With this, I would like to stop this part. Okay, not exact in time, and if you have no specific question to this, again, it makes fun to work for the water industry. Not the low budget is a very critical limitation. So I think I'll switch off. So, and okay, and now I will not use the projector. I will try to find medium technique, microphone, projector off. Yes. And where is no. It's here. This is In this second part, as announced, I try to summarize and will focus you a little bit on things I would ask in the examination. Note, with the examination, we have time, maximum 1.5 hours, normally 1 hour is enough. What you need for this exam, you need yourself first, yes, with a clear idea about the answers, and you need a pen and you need a pocket calculator. No more. Please, no script, and also not the notes from maybe you have on your handy. This was so surprising for me, not here at the university, also an industrial course on examination. I don't think, oh, guys, they must concentrate to give the answer. They permanently are checking the emails, no, nothing. And on the screen, all the texts. It's not a recommendation. Good. And I have 3 pages in landscape format, and I will bring some notes, and we will discuss. Again, if anything is not clear, or if anything you cannot understand, ask. This is a good situation for answering questions. The first part is to cover the general principles. From time to time, it's good to remember the things, what we are doing if we run a borehole measurement. If we run a borehole measurement, we normally produce logs. And the produced logs describe or give an information about the formation as a continuous information and as a quantitative. Quantitative, it means we have numbers. We have a count rate, we have a resistivity, we have a slowness, or other things. Geologist describes a rock. It's porous, it's more or less porous, it's shaly or so. Our problem, what we have an indirect information. It means with our results, with gamma indication or with resistivity, we have no direct answer. What's the sugar content, or what's the water saturation, or what's the porosity. So this results need of any interpretation or any calibration. It's not all what we have. If we are in a good situation, we have not only our logs, we have cores. Cores are only small sections we cover. This is not continuous, only it's not really a point, it's only a point information. But, and this is the positive part, it's normally a direct, that's okay, yes, information. For example, we have the porosity, indirect, for example, we have resistivity, and so on. Also density in our understanding is an indirect information because we will derive from the density the porosity, not the density itself. So we have this connection and we have the ability to calibrate. Of our logs. Core measurements have a second important information you derive from core measurement parameters for the interpretation. Who knows such parameters? We have a core and we derive important parameters from permeability as one. Permeability is a very special, yes.
Also saturation.
Exponents, there's exponents, the M and the saturation exponent are two parameters for the core measurement. And it's a simple parameter, but it's so important. It's the grain density. Remember, our porosity determination from the density means grain density. We have more, not only the cores, we have, do not forget, we have also cuttings. And these cuttings are the third source of information. From the cuttings, we derive lithology, minerals, not mineral content, not an information what type of minerals we have to expect. And this is important for creating our rock model for the interpretation. We have seen in this modern interpretation tools the most critical point is, or input is, define your model. Tell the computer program we expect there is anhydrite, there is dolomite, there is limestone or talc, there is anhydrite and there is sandstone. Cuttings can give you some of this information for free, not directly for free. You must have a geologist on site, but this summary is so low that it's practical for free. So, that was not a good comment. But true, yes. So these are the general principles, and the second part is looking on our toolbox, our methods, and the derived information. This was the first. Now we could create a long list. You have some summary also in your material. I will note only I will note what I think is important. We have here the methods, brief, what's the principles. This is a little bit stronger directed on the questions, and the application. Methods. What's the best to start? Yes. You know all the questions now. Okay. Yes. The Caliper. Normally it's the start. The principle, we must write a long text here. It's normally the whole diameter as a function of depth. We have 4 and more arms, and we remember there was also an acoustic caliper measurement, but the standard are the mechanical tools. Looks not very good. So, application. Stability of the correction of measurements. Correction of measurement, again, to understand it, think you have a gamma-gamma density measurement and you have an enlarged caliper. The gamma-gamma tool is looking very, very shallow, and it measures the density of the mud, and it has to do nothing with the density of the formation. Therefore, the caliper log is important for this problem of black hole detection. We can write it here. And for the drilling engineer of higher interest is volume, yes, volume, and this is for cementation. So it's a mixture of applications in the well log interpretation, and it also gives, we have seen, very helpful information. Mud cake and pyramids and other things. The next, now I will make a recommendation. Is the gamma log. What's the principle? The gamma log. The gamma log we measure shale content. I would write shale content here. The measuring principle is detect 3 elements. Detect uranium, thorium, and potassium as the source of the gamma radiation. This is the principle of our measurement. Let me check. Yes. And where we have it, we find it in the clay minerals, in feldspar, in mica, and also other things, and of course also uranium ores. We find it also monazite as a high thorium. So the application, we have the application as at first shale content. There are more. This is dominant.
The lithological profile in general.
Sorry?
The lithological profile.
Lithological profile. And if we have a spectral measurement, therefore for the principle, the 2, we have an integral and a spectral tool. If we have a spectral tool, we can, from the thorium, divide it by the potassium, the clay type, and from the uranium, we have an information with respect to organic components. And and source. The uranium channel is the most important gamma channel for people looking for shale gas and shale oil. This is the source indicator, and therefore it makes sense for this application only to run the gamma spectral log. So, I think you can follow what we discussed. So, if we speak about the gamma log, then next the gamma. It's not better. Gamma. So the gamma log, principle of the gamma log. We have a source, a gamma source. We have an interaction with the material, and we measure with the gamma detector. Interactions, we use two types. Dominant is the Compton effect, and the photoelectric effect. And with these two types, we have also a direct link to our applications. From the Compton effect, we get a density, and photoelectric effect was a tool more directed on which type of mineral we have. So it's more just minerals. The density is the key for the determination of another parameter. This is the porosity. This is the porosity. In the next part, we come back to this, how we determine the porosity from the density. At this point, we will remember what's necessary. We measure a gamma density, and we need the matrix porosity, and we need the fluid matrix density, and the fluid density as an input reduces. So that's okay or not? Yes. Good. Next, look at the yellow pattern. It's a neutron. Neutron blocks. We have a neutron source. It could be a chemical source or as a neutron generator. We have again interactions, and we have a detector, mostly a neutron detector. Again, to understand the principle, it's important to have a look on the interactions. The most important interaction is the elastic scatter, because this was controlled by the hydrogen with a high probability for the slowing down of the fast neutrons into a turbulent or epiturbal region. We have also some other interactions we have not discussed with this in detail. We have a secondary gamma radiation. Remember, this was the capturing effect, and this was the effect of inelastic scattering. And from this, we can derive, this comes here. Secondary gamma radiation. Elastic scatter, the application is porosity. But normally limestone calibrated. So this was the most important part of understanding Newton measurement. Newton measurements have a specific kind of calibration. They are reference to a limestone, and the limestone is water saturated, and out of this we get the answer. Conclusion was, if we have no limestone, we have another reservoir, we must apply a more or less small correction for a sandstone or for a dolomite. If we have shale, our specific friend, in the formation, we have a very strong impact from the clay-bound water because hydrogen content is high. And if we have gas, we come back also to the gas detection. Then the concentration is less compared with the water as the reference for the calculation, and we have this crossover. With with this, we get some elements. Carbon, oxygen was important, and sulfur was also important. Sulfur was important because sulfur is a good indicator for anhydride. This is dominant, and this is dominant here. We will not forget at this point for the applications, the two are combined. We have all this overlay, the cross-plot techniques, and this matrix inversion calculation was all a combination. So, and then we have one more. We have one more. This is family. This is acoustical. In the standard tool, we have a transmitter and then a wave propagation, and we have different receivers. What is our direct result? The measurement normally for the standard application is a slowness. The slowness is 1 over the velocity. Careful, the units, the slowness is therefore given in milliseconds per foot or microseconds per meter or microseconds per foot, what you prefer. So it's the inverse of the velocity and is directly what we get. Application. Application in our more narrow understanding is porosity. For the porosity, we have Wiley's equation. And we will not forget we can derive mechanical properties, Young's modulus, and support seismic. This was the original function of an acoustic log. But dominant for the porosity determination is the combination of the two modular measurements. What's the next? What you miss? Resistivity. For the resistivity, in general, it's necessary to remember if we speak about the resistivity, we must reference it to the region it's invading or the non-invading. So this is important for the other measurements. This was not because the depth of investigation is very limited. For these, the most important is to find the resistivity nodes. Yes. Yes. So, resistivity as a general term for a group of measurements, we have resistivity tools, they measure with electrodes, for introducing the current and picking the voltage, and from this we get the resistivity. And we have a second type. The second type are conductivity tools or conduction log. They measure with antennas. And we get conductivity, this is 1 over resistance. The field of the application is also part of the principle, water-based mounting. Also, oil-based nut. It works in water-based, but also in oil-based nut. So this is more general. I forgot one important note. Neutron lock, gamma lock, and gamma lock are working in case and in open wells. So now we have this. Typical principles are here. Unfocused or focused box tools. This is typical autolock. And micro box or microspherical focusing lock and all this. What's the application? We derive from this resistivities are larger log and so on, and from this we derive resistivity, like micro-log and other micro-tools. This is what we measure. From the measured curves, and this is the consequence then, because we have this zonation invaded and non-invaded zone, by the processing step we derive from this and from this together two fundamental resistivities, RT and for the invaded zone RX. This is the formation. And this is the invaded zone. And with Archie's equation, if we can apply Archie's equation, this in the interpretation section we speak a little bit more about this. We derive water saturation, and here the saturation in the invaded zone with respect to the mud filtrate, which displays the original fluid. It's okay. And the last, what we will discuss here as briefly NMR. Not too much about the principle. This is this relaxation process. With the decay time T2. What we derive is a partitioning of the water. More precisely of the fluids. We get clay-bound water, then the bulk volume irreducible and the bulk volume movable with the T2 part with three peaks. And from this, as one important application, estimate of permeability but needs calibration. In the equations there was such a parameters, codes parameter and calibration. Remember our first notes for measurements. So with this we have, I think, our tool together. And the next, what I would like to bring as a kind of a the summary is in your material. In your material, can I have a look on the? Oops, this is. If I find it, it would be good. If not, yes. 73, page 73. Make you a note. This is an overview summarizing what we summarized here. What are the main dominant applications? So, and with this, let's go to the interpretation, and with this last part, interpretation, also answers the question why we need pocket calculators. So, and now some words about the interpretation. Yes. We have a general line, or we have some steps. We must go from a lithologic description particularly also shale and non-shale sections. Then we pick the reservoir zones. And if we have the reservoir zones, we start with the interpretation, and normally first the porosity, and then the saturation, maybe also some about permeability and mobility of the fluids. So this is our normal way. And now is the question, lithology. Lithology of our tools. Gamma. It's the only one. It's a dominant, yes. We have more to separate sand, shale, spontaneous potential, yes. And
that measures for various regimes and
yes, so SB. And
also on the Caliper. Again.
Yes, Caliper. And we will not forget, we also have the possibility neutron and density. We have this typical crossover with a high neutron porosity, and it gives also a good indication. So, if the lithology is, I must always check it, if we understand the term lithology, also in this direction, we will find permeable zones. Then we have as the most indicative group of tools for permeability or for permeable. So not an NMR. NMR is the trial to determine the permeability. What indicates permeability at permeable zone in profiles? Best. Resistivity, yes. If we have a separation of the resistivities. Good.